In this series of podcasts, we're going to learn how to find the limits of trig functions. Our objectives, I'm going to talk about the bottom two there. We're going to learn some special limits of trig functions, techniques to find limits of trig functions, and we're going to learn another analytic technique, and that's the sandwich squeeze theorem. It's useful for trig functions. It's also useful for other functions as well. Rather than teach it in both analytic and trig functions, I saved this one for trig functions. Before we look at the sandwich or squeeze theorem, let's just review what we know so far about trig limits. All right, so we know that sometimes we can use direct substitution for trig limits. And when we do that, we just plug in whatever value x is approaching. And in this case, the limit as x approaches that value is going to equal the function at that value. But we know sometimes we have an indeterminate limit. And we can't use for an indeterminate form when we have 0 over 0 is what we end up with. We can't, and if x is not defined for the domain of the trig function, we're not going to be able to use direct substitution. So for example, if we wanted to find the limit of tangent x as x approaches pi halves, well, tangent's not defined for pi halves. Remember, tangent is equal to sine x over cosine x. And at pi halves, cosine x is 0. Right? So if we were to find tangent at pi halves, we'd end up with sine pi halves over cosine pi halves, and that would be a problem, right? Because that one would be 0. In this case, though, it's not indeterminate because sine pi halves is 1. So this one would just be a does not exist. Right? So the limit here of tangent x as x approaches pi halves, that would just be a does not exist. So sometimes we can't use substitution. We're going to learn some other techniques that we could use with trig functions when we can't use substitution. Nothing would help that limit of tangent x as x approaches 5 halves, however, or as x approaches pi halves, however. No matter what, that's going to be does not exist because of the 0 in the denominator, and there's no 0 in the numerator. So let's find this one. Here's one we could find for pi fourths. All right, so we have the limit of theta times tangent theta as theta approaches pi fourths. This is one where we can use substitution. So we can find this limit using substitution. And make sure, by the way, you're going along in your notes and filling things out. I don't always have the notes sitting right next to me. There we go. That looks a little bit more like the word substitution. All right, so let's plug in. And we know as soon as we go to substitute, I can drop the limit. All right, so we have pi fourths times tangent pi fourths. Let's draw a reference triangle. Pi fourths is going to be halfway between 0 and pi halves. Pi fourths, remember, is same as 45 degrees. It's a fourth, right, of 180 degrees. Right? And this is the 1 square root of 2 special right triangle. Right? So tangent, as a little reminder, uses opposite over adjacent. Right? So the opposite side is 1. The adjacent side is also 1. Right? So tangent pi fourths is going to be equal to 1. I'll write that down over here too. So we have pi fourths times 1. And that's just pi fourths. All right, so here's one where we could use substitution, right? Because tangent is defined at pi fourths. How about this one? Let's try substitution here first of all. So attempt number 1, try substitution. All right, so now we're looking at pi halves. All right, so cosine pi halves squared, as I'm moving, so that sound was me moving to the left and nearly tripping, but I am okay. That would not have been good. All right, so there's pi halves, right? And we know that that particular point, if we're thinking of the unit circle there, would be the point 0, 1. So cosine uses x, and sine uses 1, right? And that's a good way to think of it when you're talking about the quad angles, right? So cosine is the x, right? Because it's the adjacent, so it's going to be adjacent to the x-axis, so it's the x. Sine is the opposite, right? So it's along the y-axis, it's going vertical, so it's going to be the y. All right, so whether we square 0 or not, that's still 0. Now in our denominator here, right, sine theta, that's 1, right? So now I've got 1 minus 1, and that's going to be, actually I'll write it in, 1 minus sine pi halves, which is just 1 minus 1, which is 0. So this trig, the substitution did not work, right, because this is an indeterminate limit. Let's try something else. Well, I give you a big hint right here. Let's try Pythagorean identity. Maybe that will help us. So part number 2, let's algebraically manipulate, and that's what all those techniques we learned in the analytical lessons were. Algebraically manipulate using Pythagorean identity. Right, so reminder, sine squared theta plus cosine squared theta is equal to 1. If I subtract sine squared theta from both sides, right over here so I don't run out of space, cosine squared theta is equal to 1 minus sine squared theta. Let's replace cosine squared theta with 1 minus sine squared theta. Maybe that will work. I'm going to switch colors because I need to like write smaller or something. All right, so we have the limit as theta approaches pi halves. So now we're going to replace cosine squared theta with 1 minus sine squared theta over 1 minus sine theta. Well, that's a difference of squares in the numerator. I could rewrite that. So we have the limit as theta approaches pi halves of 1 minus sine theta times 1 plus sine theta divided by 1 minus sine theta. And now we see what the problem is. Okay. We have a factor of 1 minus sine theta in the numerator and the denominator. So, whoops, that's not what I intended to do. I really have to remember to lock some of these things. Let's see if I can lock it now. Because I'd like to move the green writing. Lock in place. My secrets. Letting you know all my secrets. I'd like to move the green writing because I am running out of space. And I try not to extend the page, because then it makes the writing smaller and smaller, and then it's harder for you to see. All right, so now we have the limit as theta approaches pi halves, and my theta is looking more and more like a 6. We can cancel those out, so that's just 1 plus sine theta. And now I can substitute with ease, because there's no way they can be indeterminate, because there's no denominator anymore. All right, so now I'll just substitute in. We have 1 plus sine pi halves, and we know sine pi halves is just 1. So that would be 1 plus 1, which is 2. That's our limit. So here we saw 2 different techniques in this particular podcast, right? We saw where we could use substitution in the first example, and we saw where substitution did not work because we had an indeterminate limit, as I'm moving all these things, and we had to use some algebraic techniques. In this case, we used Pythagorean identity to help us out. And as we go through these lessons, sometimes Pythagorean identity is going to be just what we needed to be able to find our limit. And sometimes, where on earth did, oh, this 2 goes here. And sometimes that's just not enough. We're going to need some more techniques. And before we can learn some techniques, we're going to learn a little bit about a special little theory called the sandwich or squeeze theorem. We're going to learn how to use that. So bye for now, and I'll see you in the next podcast.